Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In today's homework problem, you were asked to draw three major resonance contributors for the molecule N2O. The linkage pattern is shown here, and you were tasked to rank them in decreasing contribution to the resonance hybrid. You were asked to justify your answer fully. The molecule N2O is given the linkage pattern NNO, and in order to solve this, you must generate a Lewis structure and formal charges so that you can begin electron motion and generate the other resonance contributors. So if we're going to draw the Lewis structure for N2O, we need the total number of valence electrons. So total number of valence electrons. Total number of valence electrons for N2O is 5 for one nitrogen, 5 valence electrons for the other, and 6 for oxygen, a total of 16 electrons. If we start, we got nitrogen has 5. 1, 2, 3, 4, 5. The other nitrogen has 5. 1, 2, 3, 4, 5. And oxygen has 6. If we start joining up the electrons, so we join up the electrons. If we join up the three bonds here, we get 2, 4, 6, 8. The N nitrogen now is 2, 4, 6, 8. The middle nitrogen has 2, 4, 6, 8. Both nitrogens are happy, but oxygen needs 2 electrons, so I can dump in the 2 from the nitrogen in a dative coordinate bond to make a single bond. Trying to get 8 electrons around every atom, I was able to get this structure. So let's show that one more time. I'm not sure if that was easily visible. Again, nitrogen had 1, 2, 3, 4, 5 electrons. Nitrogen had 1, 2, 3, 4, 5, and oxygen had 6 electrons. If I start sharing with nitrogen, nitrogen now has 5 plus 1 is 6. And if we share again, we're up to 7. If we share again, we're up to 8. 2, 4, 6, 8. This nitrogen 2, 4, 6, 8. So we dump in the coordinate bond. That makes a single bond here, triple bond between the nitrogens. Check to make sure you've done it correctly. You should have total number of valence electrons of 16. Let's count them. 2, 4, 6, 8, 10, 12, 14, 16. Everything checks out okay. Now I'm going to label my 2 nitrogens, the N nitrogen, nitrogen alpha, and the middle nitrogen, nitrogen beta. If I do formal charge of nitrogen alpha, I get formal charge. We know nitrogen has 5 valence electrons. If we count it, we see we have 1, 2, 3, 4, 5. The lone pair gives you 2, 1 for each bond. 5 minus 5 is 0. Formal charge of nitrogen beta. Nitrogen beta, the middle nitrogen. 5 valence electrons. There's no lone pairs, but we get 1 for each bond. 1, 2, 3, 4. 5 minus 4 equals plus 1. And now we can do formal charge of the oxygen atom. Oxygen has 6 valence electrons minus 3 lone pairs. That's 2, 4, 6. 1 for the bond. That's 7. 6 minus 7 equals minus 1. The net charge is 0. Zero is what we should have. And so what we have, if we look at this, is +1 on this nitrogen and -1 on the oxygen. Okay, so I'm ready to go from here. I have generated my first structure, my first resonance structure, and I can evaluate its validity based on the question which says draw 3 major resonance contributors. The word major emphasizes the fact that we're going to try and get filled octets around every atom if possible. So I now can draw that resonance contributor again. It had a triple bond on nitrogen, single bond to oxygen. There was a -1 charge on oxygen and a +1 on the nitrogen. Now, if I count electrons around my atoms, I see I've got 2, 4, 6, 8 around the left-hand nitrogen, 2, 4, 6, 8 around the middle nitrogen, 2, 4, 6, 8 around oxygen. So I've got filled octets, and that's a good situation. We're ready to begin, and so what I'm going to do now is follow my arrow rules, which you copied down in a previous lecture. And the arrow rules simply state that you generally move electrons away from negative charges towards positive. You're only allowed to move lone pairs and pi electrons. So I'm going to dump this lone pair in. And that'll become a pi bond. If I do that, I've now got 2, 4, 6, 8, 10 electrons around nitrogen. That's not allowed. So I'm going to move one pi electron pair out and create a new lone pair on the nitrogen. If I do this, I get this. Okay. Now we need to calculate formal charge at this point. And the formal charge of my nitrogen beta, and I'll rub this off, but you could do this, formal charge, and we're going to use the same designation. Nitrogen alpha will be the end one. 5 minus, what have we got? 2, 4, 5, 6. 5 minus 6 is -1. Formal charge of nitrogen beta equals 5 minus 1, 2, 3, 4. 5 minus 4 is +1. And then oxygen, formal charge, oxygen. 6 valence electrons minus, if we check this, 2, 4, 5, 6. 6 minus 6 is 0. My net charge, add this up, and you get 0. And that's the way it should be. So we've got a -1 this time on this nitrogen, and a +1 on the middle nitrogen, and a 0 on the oxygen. Okay? So we'll keep this open. We're going to erase that now, and we'll clear it off for the next structure. So we've got another resonance contributor. We know we're on the right track if we're maintaining 8 electrons around every atom. Sometimes you can't get that, but you should try, because the question did ask for major contributors. And what we have here on our next resonance structure is, I'm going to actually violate my own rule now, partially violate it. The rule for arrow movement suggested you move away from negative charges towards positive. If I do that and bring this lone pair back in, the bonding between the nitrogens, the lone pair on the nitrogen, if I move that in, I'm going to be going back to this original structure. Now, you can do that, but we've already drawn that structure, so there's no point. But I am essentially going to move electrons away from a more negative atom towards the positive. I'm going to bring in a lone pair from a neutral. And it's attracted, electrons are attracted to positive, so I can do that. I'm going to bring that lone pair in from the oxygen. And if I do that, I'm going to get a triple bond between the nitrogen and oxygen. And that's 2, 4, 6, 8, 10 electrons again. So I'm going to be forced to move a pi electron out away from the 2 nitrogens and create a lone pair on the end nitrogen. That will produce this structure. And there we have it. If I check the formal charge on this structure, again calling the N nitrogen, nitrogen alpha, nitrogen has 5 electrons. I count the lone pairs, that's 2, 4, 6, plus 1, that's 7, minus 7, 5 minus 7 equals a minus 2. Formal charge on nitrogen. Nitrogen has 1, 2, 3, 4, 5 minus the 4 from the bonds. 5 minus 4 equals plus 1. Formal charge of oxygen. Oxygen has 6 valence electrons from the periodic table. Lone pair counts as 2, 1 for each bond. 2 plus 3 is 5. 6 minus 5 equals plus 1. Add up my net charge. Equals 0, the way it should be. And so this is a minus 2, plus 1, and plus 1. Now we can begin. We can erase our formal charge calculations, and I would have kept those on the answer if I had to show my work right under it. And I will label each of these. And if you want an idea of how you have to explain this and what you have to draw on a quiz, certainly you should be looking at the old quizzes. So I'm going to label these molecules A, B, and C. Now the first rule states, rule number 4 in our rules for writing resonance structures, states that structures with filled octets are more important. I'm going to get rid of my arrows if I can. Structures with filled octets are more important than structures without. Okay. So I check each structure, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And if you count the electrons around every structure, you will find every structure has filled octets. So with regards to rule 4, we can actually state that all structures have every atom with filled octets. Okay, this I can do. Then I would begin analyzing it from rule number 5A in our rules for writing resonance structures. Rule 5A states that structures with less charge separation make greater contribution to the resonance hybrid than structures with more charge separation. If we compare structures A and B, they both have a -1 and +1 charge separated by a distance of 1 bond, if you like, even though they span a double and single bond. But if we look at structure C has much greater charge separation. So we can indicate that this rule is violated for structure C, and we can say C is the most minor contributor. Why? Well, there are a lot of reasons we can mention here. It's the most minor contributor. Why? Well, one, the most important reason is it has greater charge separation. Now you would write this out in complete sentences. I'm just using smaller point form. Greater charge separation. Two, These are also reasons, although I agree they are much more minor than the charge separation issue. But it also has an unfavorable -2 charge on one atom. So it has an unfavorable -2 charge on one atom. 3. It has an unfavorable adjacent positive charges. And lastly, 4, the negative charge, your negative charge, is on the less electronegative atom. I'm going to just use capital EN for electronegative. Less electronegative atom. So if you look at these 4 points, they are a justification. Remember, the question said justify your answer fully. This represents the total justification of why C is less a contributor than A and B. Note, however, that point 1 is the major reason. It is the real reason. All the other points we're drawing your attention to, although they make the structure less and less favorable, they are not as important as the greater charge separation. Okay, now in terms of the next few rules, since structures A and B have same charge separation, we have to move on and consider rule number 5b. Rule 5b states that structures, resonance structures, that place the negative charge on the more electronegative atom make greater contribution to the resonance hybrid than those that don't. So the question is, who's more electronegative, oxygen or nitrogen? If we look at this structure, we see that oxygen in A has a negative charge, but the nitrogen in B bears a negative charge. Oxygen is more electronegative, hence structure A makes a greater contribution. You can say that. A is a greater contributor than B. A greater contributor to the resonance hybrid than B. Why? Well, let's take this up to the top. Rub some out if we can. Make some room. A is a greater contributor to the resonance hybrid than B. I'll bring this right up here. Because in A, I'm going to use capital EN for electronegative, the more electronegative oxygen bears a negative charge. A negative charge. Okay. So all that remains after I've given my full explanation is to give my ranking. I believe I asked in decreasing order, which means you start with the greatest first. So A is the greatest contributor. Who's greater than B? Who's greater than C? Now you may have a different ranking because you may have drawn them in a different order, and that's fine. I'm not picky about that. But what I do expect is a complete explanation. You will draw your resonance structures, show your formal charges. You will write out your justification and explanation stepwise, starting with Rule 4 by looking at filled octets, then looking at charge separation, then looking at who bears the electronegative charge. In the minor one, you will list the extra things that are wrong with it if they are there. All right? Or I may dock you. Okay. This is a solution for the homework assignment N2O. Thank you very much.